Hello and welcome to the last part of our course. So here we will discuss sequential circuit design. So previously we studied combinational circuit design where we had used all gates, logic gates, and input to that circuit was processed by the series of logic gates and some output was given out from that circuit. And we studied how we can actually design a circuit when a problem is given. Now, what is the difference in sequential circuit? So, we have already introduced the memory elements. So, the flip-flops form now the basic ingredients of the sequential circuit, as the gates used to form the basic elements of the combinational circuit. So, when the flip-flops come into the picture in a circuit, then the memory function, which is a new function which the flip-flops are giving us, so that memory functionality, the memory feature gets presented in the sequential circuit design. So when you have to develop, or when you have to design a circuit which has to take into account the past state of the circuit in order to give the new state, in such problems we are actually dealing with sequential circuit design. And some standard sequential circuits we have seen, registers and counters. We have also understood what is synchronous and what is asynchronous. So now we are at the age at that stage where we can actually take up a problem and go ahead and design a new sequential circuit for the given problem. So this is the what the design engineer needs to develop the skill of. Whenever a new problem is given, the design engineer has to look at the problem and have the skill set to develop a circuit which will implement that problem or implement the solution of that problem. So here we come with the sequential circuit design. So let us first do something which is like how to analyze a given sequential circuit. So one sort of analysis we have already seen, which is the analysis using timing diagrams. Now we will analyze in a different method, which is the analysis using state tables. So the table that you are seeing in the right hand side is the state table, and just note the columns of the state table. So PS means the present states, IP is the input, NS means the next states, and OP is the output. So obviously, even if this PS, IP were not written, you could understand by looking at QA, QB, U, QA plus, QB plus Y, that these first two are the present states, QA plus and QB plus would be the next states. U of course is the input and Y is the output. So what happens in a sequential circuit? In any sequential circuit, here one example circuit is given, but such interconnection of between the flip-flops and the gates, certain circuits can be given to you and you can be asked to find out the state table. If you are asked to do that, you need to exactly do what I am going to show you now. So first you have to first you have to tabulate the present states and the input, and the tabulation goes in the order of binary numbers, as you can see by looking at this present states and input. So there are two present states and one input, so total there are three binary bits actually, and so you will have 8 different combinations. So these 8 different combinations has to be written down in sequential manner, in order from 000 starting to 111 ending. So in order you will write down. So this way you have written down. Now what the you have to fill up the columns of the next state and the output. So the what to do, you have to simply see where your U is in the circuit, where your QA, QB is in the circuit, and if your U, QA, QB has this combination which is 0 0 0, then you see what would be the next state of the flip-flops. So this you have to analyze, and what would be the output from the circuit. So this is what you need to analyze only. So let's see for 0 0 0 what it will be. So for 0, if you put 0 here, so in U you are putting 0, your QA is 0, your QB is 0. Suppose you are in this state QA, QB is 0 and you have given an input also of 0. Then you can see that what is this D. So whatever this D is, that will come to QA plus, right? So that we know. So this is the D flip flop, which is very easy. What QA plus would be? QA plus would be D. So what would be the D when U is 0? So this is a XOR, right? So the XOR, when one of the XOR inputs is 0, then the other input, whatever it is, it passes through the XOR. So let us see what is the other input. It is the AND of these two signals. So what is this signal? This signal is coming from Q bar. This is 1. So this is 1. Let me choose another color here just to show the intermediate states. So this is 1. What is this signal? This signal is coming from QB. So this is 0. So ultimately you get 0 here and 0 here. So QA plus would be 0, right? Because D is 0, QA plus would also be 0. Now you see what is this D. This is basically, this is 1. So this 1 is coming here. That means QB plus would be 1. It's very simple. What is Y? Y is getting this 0 here. This is 1. So this 1 is coming here. So 1 and 0 having a NAND operation here, it will give rise to 1. So that is the case for 0 0 0. See, in this way you have to analyze the circuit. It will take some time, but you be diligent in your analysis, otherwise you will do mistake. What would happen when it is 0 0 1? So again you would do the same analysis by replacing this 0 0 with 1, and then you see what happens to the entire circuit. So the analysis is done for the first two. You see that we have already figured this out, that QA plus would be 0, QB plus would be 1, and Y would be 1. In the situation when it is 0 0 1, then QA plus becomes 1. So QB plus, of course it will still be 1 because QA is 0, this is going here, so QB plus would be 1, and Y would also be 1. QA plus has changed because your what is happening here, QB is 0, so it is, and it is coming here as 0, and your QB, so this is 1, right? So when this is 1, actually this is coming as 1 here because this is 0. So that's why this 1 is coming to QA plus. So the QA plus is 1. So in this way you have to analyze. In this way you have to analyze. You have to look at the present state and the input combination and figure out what is going to be the next state and the output. Okay, so this is all that you have to do in order to prepare the state table when a circuit is already given. So let us complete this exercise. So just observe and verify that these entries are correct. So this is how it ends, and you can verify on your own whether the state table has been correctly written down or not. So after you have written down, after this exercise is complete, so now there is one important understanding one needs to make. We need to understand this thing, that you just note that the output remains same for the present states. So there are 4 present state combinations: 0 0 0 1 1 0 1 1. you notice that for each of these states, present states, the output remains same, the output does not change. So when the present state is 0 0, the output is 1. For both these rows the output is 1. When the present state is 0 1, again the output is 1. When the present state is 1 0, the output is 0 for both the rows, no matter what is the input. So the output is not depending on the input, the output is only depending on the present state. So this is what needs to be noticed here. So when the output depends only on the present state and not on the input, then this sort of sequential circuits are called Moore circuits. Moore circuits are those sequential circuits or Moore machines. You will notice this term. There are circuits, there are machines, there are diagrams, all these things will come. But whenever we say Moore, it will mean that the output of the system does not depend on the input explicitly. Of course the input is driving the output because the input is changing the states and the present state is making the output. So there is an influence, of course, but the influence is not direct. The direct influence is of the present states. So when this is the situation, then the circuit is called a Moore circuit. So remember, fundamental thing is this, that the output does not influence the input, sorry, the input does not influence the output directly. So that is the Moore circuit. Now we will change things a bit in the circuit and we will try to influence the output directly. So this is what we have done. So when we have taken the input direct with and made a direct connection with the logic gate in the output, then this becomes what is called a milli circuit, where the milli means the system output is directly influenced by the input. Then it becomes a milli circuit or a milli machine or a milli diagram, etc., etc. Milli system basically. What is a change? If you have not noticed the change, you see that in this state table, you notice the sixth row, output of the sixth row, you notice that only changes. When we have made this connection, only that output changes. But what it does basically, you cannot say now that the output depends only on the present states. This is not true anymore, because for this combination of present states, the output is different for different inputs. So the input has some influence now on the output. Obviously this is seen from the circuit. But suppose you don't know the circuit, you are only given the state table, then would you not be able to say whether you have a milli system or a Moore system? Yes, you will be able to say by observing whether the output is depending only on the present states or it also is influenced by the input or not. Okay, so that is what you need to note from the state table. So this is a milli state table, the previous one was a Moore state table. This is a Moore state table, this is a milli state table. Block diagram wise, in this when we have a block diagram, so now we can actually talk in a more general sense. We can shift our attention from circuits which are developed using flip-flops and gates, but talk in a more general sense about Moore and milli systems, and such systems are basically called machines, state machines. So these state machines are conceptual things. Please understand that these are conceptual things. So when this what is the concept? The concept is just taking out the abstract from what we have just discussed. The abstract thing is this, that when you have inputs and outputs from a system with a memory element, and that gives you the states, the idea of states. Whenever there is a memory, you will get the idea of states, otherwise you will not get that idea. So this sort of a situation presents you a mood machine. Here in the mood machine, the output depends only on the present states. That's all. How you are going to implement a mood machine? That is a different question when you are only looking at machines in the abstract sense. Of course, we know that using our digital electronics, logic gates and flip-flops, we will be able to implement a mood machine. But as such, mood machine is a abstract idea or a more general idea. Something else, some other sort of systems or some other sort of physical system can also give you the behavior of a mood machine. Please make that clear in your mind. But normally, generally and mostly we use digital electronics to develop such mood machines and also mealy machines. In mealy machine, the output is directly influenced by the input. You see, the output depends on both the present input and the present states. The input now has a direct connection to the output combinational logic. So this becomes a mealy machine. Now we will look into what are called the diagrams. So the mood diagram and the mealy diagram. So whenever you have the state table, now you look at the state table. So we if there is a actual system or not, we are not bothering right now. Right now we are bothering about the state table, which gives us a clear information about the dynamics of the system. Dynamics of the system means when I am at a particular state and some input has come, where in which state I am going to go, what would be my next state and what would be my output. So this information is the dynamics of the system. So the state table presents the entire dynamics information of the system. So this is a mood diagram because the output depends on the present state only. So that is why it is a mood diagram. And in this case, how we write down the state table in a more general way, that is what is given here. You see, in this the present state is not like QA, QB or like that. It is simply some state S0, some state S0. Okay, you have to from a problem given, you can actually identify some states which you will need in order to solve the problem. When we actually go into solving one problem, you will understand this. But let us now just concentrate on this fact that whenever you are given a problem or whatever, you have already extracted what could be the states of the system. When you have extracted what could be the states of the system, you can denote them from as S0, S1, S2, S3 like that. As many states you would have, you can give the denotions accordingly. Also, you would be able to understand that if you are in a particular state, given a particular input, in which state you will go. This also you will be able to understand from the given problem. What you are doing in the state table, you are presenting that information in a structured way. That is all you are doing. So here, when the information is presented, then how someone who is looking at the state table will read the information. Let us read that so that you are also able to read it. So here we have actually identified several states. So in this example or in this illustration, we have identified 4 states: S0, S1, S2, S3. Corresponding to each of these states, you will have a row of the state table. Corresponding to each of these states, you will have a row of the state table. So the present state is the first column. In that you have given all the states S0, S1, S2, S3 in some order which you have preferred. So this order is not like S0 I have given here. I could give S1 also, then S2, then S0, then S3. It's up to me. But normally we give it in an order which is beneficial for all of us to understand, and this is the most intuitive ordering of the states. So S0, S1, S2, S3 we have given here. Now what we are reading in this way, that when I am at S0, if my input is 0, u is 0, then my next state would be again S0. If I am at S0 and my input is u equals to 1, then my next state would be S2. If I am at S0, then my output would be 1. So the output is depending on the present state only. Hence it is a mood machine, mood state table, and what you are seeing in the right hand side is the mood diagram, which I will explain just a bit. So that is mood diagram. Similarly, the second row, how you are reading, when the system is at state S1, if it is receiving input equals to 0, it is going to next state S2. If it is receiving input u equals to 1, it is going to next state S0, and when it is at present state S1, the output is 1. In this way you can read the entire table. Once the table is read, then what you can actually do, you can represent this information in a much better manner, in a diagrammatic manner basically, which gives you the information very readily. So that diagram is called a mood diagram, and that mood diagram is shown in the right hand side. Here it is simply some circles and arrows, that's all. Each of the circles represent the present state or one of the state. So each of the circles represent one state, not the present state, sorry, it represents one state. So if there are 4 states, you have 4 circles. Each of these circles you denote by the name of the state S0, S1, S2, S3. Now in the mood diagram, since the output is linked to the state only, not to the output, not to the input, then you can associate the output with the state itself. So you know that when the present state is S0, output is 1. So in the circle of S0 you can write 1 also by giving an underline like this. So it's like you are writing a fraction, S0 at the top in the numerator and 1 in the denominator, but the representation means that S0 is the state and corresponding output is 1. Similarly, you see note the output column and note all these circles. You will see that we have associated the output of the state to that particular state. So after this, what are the arrows connecting the states? These arrows, you will see, you will note that the arrows also have some number associated with it, either 1 or 0. These are the inputs. So it means that when you are getting an input of that particular value, then a state is getting changed from one state to another. And you see, you read again, as per the table, when you are at S0 and receiving input 0, then you are again coming back to S0. So that is what is happening by this particular arrow. You see, this is a self loop. So this is a self loop. So in this self loop, the input is 0. This is read like this: when you are at S0 or when the system is at S0, it is going to S0 again when input is received as 0. It is going to S2 when the input is 1. Similarly, you can see from S1, it is going to S2 when the input is 0, it is going to S0 when the input is 1. And that is exactly what is written in the state table also. You can read the same information from the diagram, mood diagram, very easily. State diagram, and this is the mood diagram. From S2, if you are having input 0, you are going to S1. If you are having input 1, you are going to S3. From S3, if you are having input 0, you are coming back to S3 again. If you are having input 1, you are going to S2. This completes the completes the dynamics information. So with this you know exactly how the system will behave. So now if anyone says that my system is at S3 right now, can you tell if the input is given as 1, where will my system go? You will say yes, of course it will go to S2. It will go to S2, right? So if someone asks you if that my system is at S1, what is the output getting produced? You can again look into the state diagram and say that the output will be 1. So all the information is captured in the state diagram. This is the mood diagram. Now one more thing here, if we have such a situation like this, so notice the change now. So we have changed this second row. You see that S1 it is going to S2 irrespective of what is the input. In that case we can write an X in place of the input and direct the arrow to S2. X means the input can be either 0 or 1, it doesn't matter, it will anyway go to S2. So this sort of notational convention is there for mood diagram. For milli diagram, let us see now. For milli machine, this is the milli table and the milli diagram in the right hand side. The change you have noticed from the state in the state table is that the output also now has 2 columns, one column depending on u equals to 0, another column depending on u equals to 1. So the output basically changes depending on the input. For s equals to 0, for both inputs the output is 1, but for the others you see that it is changing. Okay, S1, S2, S3 again both are 0, but for S1 and S2 they are different when u is 0 and u is 1. So the next, so how you are representing the information in the state table, in the state diagram? I hope you will be able to read the state table. It is very easy. Just output has 2 columns now. There is nothing, no more difference. But the difference has happened in the state diagram. In the milli diagram, it is a bit different, and we have to read it a bit carefully now. So since the output is not associated with the state anymore, we are unable to write the outputs inside the circles. So in the circle only the state number is given, S0, S1, S2, S3, state identification. Only the state is identified there. The output is associated with the input. So now you read like this. So this arrow is saying that when you have an input of 0, then you are coming back to S0 and your output is 1. So you read from the first row of the table also, when your input is 0, you are going to S0 and your output is 1. When you can read it in this way, that this would be better, that you are going to S0 while generating an output of 1. If you use the word while, it would be better, because the output is due to the input. It is not in this way that you go to S0 and then you generate an output of 1. Then you might think that it is depending on where I am going, but it is not depending on where you are going, it is depending on how you are going. So how you are going is by the input 0. This is how you are going. So it is depending on that. So when your input is 0, you would go to S0 while generating an output of 1. Here in this arrow, you are going, when your input is 1, you are going to S2 while generating output of 1. If you are in S1, if your input is 0, You can also read in this way: if my input is 0, I am developing an output of 1 and going to S2. Okay, if my input is 1, I am giving an output of 0 and going to S0. So in this way you have to associate, you have to dissociate the output from the states completely and associate the outputs to the input. And now you can read the state diagram as per the state table. You can verify that everything is as given in the state table. So this is the Mealy diagram. Important thing to note is that the output has come out of the states and has got associated with the input, and that association of the input is also given very clearly in the state table. This is a situation now in Mealy. In Mealy, what happens, you see I have again changed the second row. So from S1 you will anyway go to S2, but the output getting generated is different for different inputs. Hence you would not be able to write X in place of input anymore, because because one input is associated with one output, another input is associated with another output. Hence you will not be able to write X anymore here. So you have to write two arrows like what I have given here, and associate each of these arrows with a set of input and output. Now we come basically with all this introduction, all this understanding about Mealy circuits, Moore circuits, state tables and state diagrams. Now we are in a position to dive into solving a sequential circuit design problem, and this is the very standard and almost the first example that is taught in a course, which is the prime number detector. This can be 4-bit, 5-bit also. We are focusing our attention on 3-bit prime number detection. 3-bit prime number detection means the numbers is limited to 3-bit only. So 000 to 111, that means from 0 to 7 you are looking at prime numbers. Whenever you are getting a prime number, your some output must be generated. So it generates high output, is given that it generates high output when binary word is a prime number. And also it is given that the count changes. So when you are at 000, you will not stay at 000 always. Your count will change to 001 at the next clock cycle. So the count changes at every clock cycle. So it is like a counter, right? So it is counting from 000 to 111. The counter we have already studied. However, there is an additional thing, that whenever the count is a prime number, it is generating a high output. So this is what we have to design. How to design this? In such designs, we have to first identify what are the states of the system. This is the most important and the most fundamental thing that you should keep in mind. If you have identified the states correctly, your half the job is done, or maybe 75% of the job is done once you have identified the states correctly. If you have done some mistake or you have not identified the states properly, then you will land in trouble. So the first step is the most important step. Please keep it in mind. In our examples, we will have more or less simple systems to deal with. Even in exams, it will not be so complicated, but the trick is there only. You have to identify the states properly. So here you can perhaps is very readily able to understand that there are 8 states. So the system can have 8 counts, 000 to 111. Each of these can be treated as a state, and in some of these states your output would be high, in some of these states your output would be low. You have to only identify those states where the output is high. So the output basically depends on the present state, whether it is prime or not, and there is no other input other than clock. So there is no additional u input here, because at each clock cycle the state is changing on its own, and in each clock cycle the state will actually eventually change anyway, but there is no additional input u here. The clock is the only input. So we have 8 states S0 to S7, and we denote the states as S0 to S7. You can denote in any fashion you want. However, this is convention, and you can understand why this is an intuitive convention. You should not write any arbitrary things. So this is the most logical way to, most intuitive way to represent 8 states. If you have 8 states, you represent them from S0 to S7. So this is the case. So now what happens? So now you have to actually tabulate these states in a state table. So this is the first task now you have to do. You have to form the state table. Since you know the problem and you have identified the states, there would not be any difficulty to formulate the state table, because you know that these are my states, and by the problem you know that when I am at a particular state, what would be my next state. This information you are having. So you tabulate the states. Right here you see that we have 8 number of rows, S0 to S7, and the next state we very simply know that it is always going to the next count. Wherever you are, you will go to the next count in the next state. So from S0 you are going to S1, from S1 it will going to S2, like that. When the output is generated when you are at a count, or you are at a state which is representing a prime number. Which are those states? Here there is some confusion with 1 being a prime number or not. We are not considering 1 as prime number. So the prime number has started from 2. So 2 is a prime number. So for S2 you are getting an output 1. For 3 you are getting an output 1. For S4 it is not a prime. S5 you are getting an output 1. S6 is not a prime. Then S7 is 7 is a prime, you are getting an output 1. So the state table you have formed. After forming the state table, you can form the state diagram if it is asked to do so, or if it is convenient for you to make the state diagram also. Because you will notice that the state diagram is not important in order to solve the problem. State diagram is only for representation purpose. So if you are asked to solve the problem, you can skip this step. If it is not asked to draw the state diagram, you can skip this step also. But if you are asked to draw the state diagram, then you draw it as per the state table. You can draw it now easily. You know the states, you know the associated outputs, and you know from which state you are going to which state. The arrows you know, the arrow directions you know. Note that here no input is there. So the arrow means it is automatically going. It does not depend on any input. The arrows are not having any inputs associated to it. That means whenever you are at S0, in the next clock cycle you will go to S1. In the next clock cycle you will go to S2. So this is basically a state diagram of a counter. This is a state diagram of an up counter, 3-bit up counter. And we have some outputs associated with it. Now what to do? We have come to this stage where we have formed the state table with the states represented as S0 to S7. Next step is that we have to represent these states in terms of flip-flop outputs. These are just some identification, S0 to S7. This does not help us in order to make a digital circuit. To make a digital circuit, the present state must be in form of flip-flop states. So since there are 8 states, how many flip-flops would you need? in order to represent all these states, you will need 3 flip-flops, because 2 to the power of 3 is 8. Each flip-flop will give you 2 states. 2 to the power of 3 is 8, so total 8 states you will be able to obtain using 3 flip-flops. Convention is that you name the flip-flop starting from A, B, C, like that. So you have QA, 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 QB, QC. QA, QB, QC you have, and you denote the states now in terms of the bits, in terms of the binary word. So the S0, you see the S0 has become 0, 0, 0. You notice the diagram or you notice the state table, you will notice the same thing as I am saying. The S0 has become 0, 0, 0, S1 has become 0, 0, 1, and likewise we have actually given a binary word to each of these states. And this binary word is nothing but QA, QB, QC. This binary word, we have to assign the MSB, LSB, etc. Each of the bits we have to assign to each of the flip-flop outputs. So QA, QB, QC is now the states. So 0, 0, 0 means QA is 0, QB is 0, QC is 0, 0, 0, 0, 0, 1 means QA is 0, QB is 0, QC is 1, like that. So now you have a table where you have present flip-flop states, next flip-flop states, and an output. In this situation, treating the QA, QB, QC, the present states, as the input, you will have 4 output columns: QA plus, QB plus, QC plus, and Y. What you need to do? You need to simply find combinational logic equations for QA plus, QB plus, QC plus, and Y. That's all. In this particular problem, there is no additional input here U. So only QA, QB, QC, the present states, are the input. So you find the combination logic equations for QA plus, QB plus, QC plus, and Y by using K-map. K-map you use, solve the K-maps. You have to solve 4 K-maps here. Once you have the K-maps with you, then you will be able to get the circuit. So the K-map will give you the equations QA plus, QB plus, QC plus, and Y. So you get the next state equations. When you have the next state equations, you can now implement using a circuit based on flip-flops. If the flip-flops are D flip-flops, then simply whatever QA plus is, that is D. So you have to make a combination circuit as per the right hand side and connect it to DA. You have to make a combination circuit like this as per QB plus, right hand side of QB plus, and connect it with DB. This is as simple as that. That is what has been done here. That is what has been done here. So you see QA plus, so we have used D flip-flops. QA plus is QA, the present QA is given here, a XOR, so this output is coming here, right, DA. So XOR of QB, QC. What is this? QC, this is QC, and the other one is QB, this is going to QB. So the equation, whatever combination circuit, combinational logic equation is obtained due to the K-map, that we have formed and supplied that to the input of the corresponding flip-flop. Similarly, you can check for DB. DB is simply QB and QC XOR. This is DB, and DC is QC bar, that is DC. And your output is QC plus. So output, you see, this is OR gate QC and OR with QA bar QB. So QA bar and QB are ANDed and then supplied to this OR gate. So this circuit will now behave as required. as required it will behave. So it will detect a prime number. Whenever the count becomes prime, you will notice an output here. So this is how you actually solve a sequential circuit problem, sequential circuit design problem. What are the steps? We have to first identify the states, form the state table, associate the states with binary words, associate the binary words with flip-flop outputs, get the next state and output combination logic equations, and then draw the circuit. So these are the steps, one by one you have to follow. Another example we will show here, gray code counter with reset. Now gray code counter, it counts periodically. So what is the objective? It has to count. So these objectives will be given to you in the problem. It has to count periodically from 0 to 7 in gray code. It has to count in gray code. The output must come in gray code. Okay. Count changes at every clock cycle by default. Count will by default change. However, there is an additional control input which is the reset control input. Whenever the reset control is pressed, count must go to 0. So you can actually reset the counter any time you wish. Whenever you reset, in the next count would be 0, 0, 0. So this is the thing. The output is the gray code of the corresponding decimal count. Output is the gray code of the corresponding decimal count. Okay, so the output must also be in gray code. That is what it is saying. So now we know, so we can define these 8 states now, because we have to count from 0 to 7. There are 8 states, S0 to S7, and we can have 3 outputs, because the output is also there, right? So the output is the gray code. So previously there was no output, as output is only the prime number detection. Here the output is the count itself. Here the output is the count itself. So there are 3 outputs, y0, y1, y2. They are exactly the flip-flop states if the states are represented in gray code. If you are representing the flip-flop states, or the state table you are representing in gray code, then these are exactly the flip-flop states. You don't have to do anything. If your flip-flop states are normal binary counts in order, then you have to actually form y0, y1, y2 additionally as per the binary to gray code conversion and find out the circuit. And the input u is u representing the reset signal. There is an input representing the reset signal. How the state table will be formed? I have directly actually considered the counts as the states. This you can do, but you have to define. So I have not given one step here, which is the definition. So if you are to write directly the state table using the binary numbers as I have written here, you have to define the states S0 to S7. So I have defined in the state table itself. You see, present state S0 I have given as 0, 0, 0. Present state S1 I have written as 0, 0, 1. Present state is S2 0, 1, 1, like this. So I have given in gray code. I have already given in gray code, so that I don't have to additionally create an output combination circuit. So I have already given in gray code. So in this way you have to define the states before writing the state table using the binary words. That definition must be very clear to the person who is reading your solution. In the matter of exam, the person who is checking your exam sheet. So this definition, this correspondence must be very clearly indicated. Either you indicate in the state table itself or you indicate outside the state table, that is not a matter of concern, but this indication must be there. So now now you can create the state table. So you have the present states, you know what would be the next states, and the next states would depend on the input also. There is a reset control input. When the reset control input is high, when it is 1, no matter where your state is, it will go to the reset state which is 0 0 0. So you see all these are zeros when the u is 1. When the u is 0, then the normal counting will proceed. And since I have represented the counts in grey code, so the next state counts are also, you see, next states are also in grey code. Okay, so this would be basically S1, this is basically S1, this is basically S2, like this. So all these are directly given in the binary word. Okay. In the state diagram, you see, in the state diagram, I have given a S0 and the output should be 0 0 0. So it is not the state, it is the output actually given here. It is 0 0 0. It is 0 0 1 when the input, when the state is S1. When the state is S2, the output is 0 1 1. Okay. So even if you had represented the states in normal binary, the output should still be like this. That's why I have given here S0, S1. I have written the states in terms of S, not exactly the word, because this is flexible. How you define S0, S1, S2 in binary, this is flexible. Which sort of binary code you want to use, whether you are using normal binary, whether you are using grey code, whether you are using this, that, whatever, it is up to you. But the output, what it should come out, that is given by the problem. The output must be as per the output table which is given here. And you also see in the state diagram that whenever the input is 1, you are going back to S0. Whenever the input is 1, you are going back to S0. And there is one from S7, no matter what is the input, you will go to S0. And from S0, S0 when it is 1, actually this should be there. This one loop have been missed. It will come back to S0, and when it is 0, it will go to S1. So this is the grey code counter with reset. So this is a state table. Now next you have to find out the combination logic equations for QA plus, QB plus, QC plus, all these. Note that QA plus, QB plus, QC plus will also depend on U. There are now 4 inputs. The 3 flip-flop presents the 3 flip-flop states, QA, QB, QC, and U also. The next states will depend on all of these. Even the outputs will depend on all of these. You find out the equations, you will see that QA plus, QB plus, QC plus are like this, whatever has been indicated. Of course, Y2, Y1, Y0, since the count is already in grey code, it is simply QA, QB, QC. And now you design a circuit using flip-flops. That's all. Draw the circuit using different flip-flops. Using different flip-flops I have mentioned here, because see, with D flip-flop it is very easy, because QA plus is simply D. Any Q plus is equals to D. But if it is a JK flip-flop, if you are asked to draw using JK flip-flop, if you are asked to draw using SR flip-flop, if you are asked to draw using T flip-flop, what you will do? What is this? This is the excitation, right? D is the excitation. So from the excitation table you get the equation of D as Q plus. Similarly, from the excitation table of JK flip-flop, you will get the equation of J and K in terms of Q plus some function. You will get, you find out what is this function. So when you have to use JK flip-flops, you have to first you have to find this Q plus, but then you have to find J and K additionally. JK you have to find additionally as per the excitation relation of JK flip-flop. Please keep that in mind, and you try to draw the circuit using different flip-flops, so it will make a practice for you. So here it ends the lecture. This particular lecture it ends. In the next lecture I will show you some more examples of sequential circuit design. So thank you for your attention. Have a good day.